Good afternoon, everyone, and thank you, Pascal, for the kind presentation. I would like to start by thanking Jean-Christophe Lacroix and Corinne for inviting me to give this lecture. So as already said and projected, I'm going to talk about electrochemistry of corrosion at the nanoscale. Obviously, I'm not going to cover all the aspects. The idea is to show, to exemplify an approach in which we are looking at corrosion at the nanoscale, including the use of electrochemical techniques, but many other surface analytical techniques. And obviously, I will focus on one aspect because I prefer to go into slightly more details rather than just making a brief survey of many things. A few words about the background. I would like to state or emphasize that corrosion processes are actually surface processes taking place at the nanoscale, and they even initiate at the atomic scale. Roughly, when one atom will leave the surface of the material, its corrosion is starting. However, the effect of corrosion, which is to produce failures of materials, are often observed at the macroscopic scale, and I'm sure you have heard many cases of big failures caused by corrosion. So understanding oxidation and corrosion of metal surfaces at the atomic or nanometric scale is really a key to a better design of materials, engineering metals and alloys, and lasting longer, which is of course very important in the present context. So the main topic I'm going to address today, which is at the center of corrosion science, but there are many other aspects, of course, that I'm not going to address, is the stability of surface oxide films on metals and alloys. The reason for that is that the best way of having sustainable alloys is to have alloys that are protected by the surface oxide films, and it's only if this is not achieved that we need to look for other ways of preventing fighting corrosion. So the data I'm going to present are based on a number of techniques, and it's really a surface science approach because we are combining advanced surface analytical techniques, and I'm going to show some of the results obtained with this technique with electrochemical measurements. We also combine these experiments with DFT modeling, although I'm not going to talk about DFT modeling today, but it's important to state that because we are looking at the phenomena at the atomic scale, we can design the proper models to do DFT calculations, which is not always the case if one doesn't have the information at this molecular level. The model that can be used by DFT might be unrealistic. So stability of surface oxide films on metals and alloys. As I have stated already, the formation of protective surface oxide is a key for the durability or sustainability of metals and alloys in most environmental conditions, and this is also in most industrial sectors. The problem with these oxide films is that if they break down, and they do break down very locally at a very local scale, or starting at the atomic layer or the nanometric layer, that can lead to a localized corrosion and failure of the material and failure of the whole structure. So the aim of the research that we are doing in my group is to uncover the relationship between oxide growth mechanisms, reactivity, and stability of surface oxide layers at the nanoscale, and of course looking at real corrosion tests to make sure that we found the key factors for preventing corrosion. Oops, using the wrong computer. So this is a sort of textbook view of an oxide passive film on a metal. So if you look at that, it seems very simple. If you put a metal in an oxidizing environment, and it's most often it will be oxygen or aqueous solution, then if it's a good metal in terms of corrosion resistance, it will form an oxide, and on top some hydroxyl groups can be adsorbed, or a 2D layer of hydroxide, sometimes a 3D layer of hydroxide. And what we call passive films are thin oxide or oxyhydroxide films that cover the metal substrate and protect it against corrosion. So it looks very simple, and this is the kind of scheme you would find in the textbook. But however, behind this simplified scheme, there are a lot of key questions that, and some of them still need to be answered. What is the oxide structure? What is the role of the surface hydroxylation, which is always present on top of the oxides? What is the surface of the interface? Because these are electrochemical processes, what is the effect of potential and time on the structure? What are the ion transport mechanisms in these oxides, which often are semiconductors, so the transport will differ whether it's an N-type or P-type semiconductor, and in some cases it will lead to the formation of vacancies at the interface. What is the nature of the defects that are formed in the oxide? What is the role of alloy elements? Because we usually don't use pure metals, but alloys. What are the electronic properties and the local electronic properties? And what are the initiation sites for localized corrosion? So many, many questions, and there is still work to do to understand all these aspects, but I'm going to cover at least a few of them today. So first I would like to show you the link between electrochemical measurements on pure metals and formation of the oxide film and the detailed structure of the oxide. So here this is the case of a copper single crystal, copper 111 in alkaline solution, and I'm sure many of you are familiar with the voltammogram, where you would observe after a range which I'm not showing today, but we have studied in many details, where you have only adsorption and desorption of OH groups, but then you arrive in a range where you form copper plus and copper 2+ oxide, and these oxides can be reduced with two clear waves in the reduction. We can of course use these to integrate the charge, and that would give one way to measure the thickness of the oxide. So what we were interested in was the growth of the oxide, and to do that we have been using extensively scanning tunneling microscopy in situ, so that is electrochemical scanning tunneling microscopy. We have seen nice examples in the presentation of Mark yesterday. So basically you use a tip, you bring it close to the surface so that electrons can tunnel from the surface to the tip or from the tip to the surface by applying a very, very small bias, and the distance is of the order of a few angstroms, and then you scan the tip over the surface and you record a map of the density of states of the tunneling current, which is a map of the density of states, and that also gives you the position of the atoms at the surface. And this can be done with very, very high resolution, namely with atomic resolution. So in this work, we use a tungsten tip, which allows us to get atomic resolution because it's a fairly rigid metal. So this is one example of a scanned area, 25 by 25 nanometers square. And what you see are terraces and steps of copper oxide. And as we started with a copper 111 very smooth surface with a degree of disorientation of less than 1 degree, you clearly see that these surfaces and steps, the steps have a high frequency, so the terraces are not wide, and this means that something is taking place because we are starting from a very smooth surface. I will come back to that. Now, we can also look at much higher resolution, and this is here the high resolution image recorded in situ. It's without filtering, and it's in the direct space. We don't use Fourier transform to get this. So this is the direct space image of the structure of the oxide that is forming on the surface. And you can see that it is an hexagonal arrangement. And this corresponds, if we measure the distances, this corresponds to the formation of Cu to O, and this corresponds to the formation of the 111 plane of Cu to O. However, as I pointed out, there are narrow terraces, and this means that the oxide is growing with a tilted angle between the orientation of the oxide and the orientation of the substrate. And by measuring the width and height of the terraces and height of the steps, which can be measured with a high precision using the scanning tunneling microscope, we can then get this model for the system with a smooth, flat copper 111 single crystal as a substrate, and the oxide is growing. So it is growing here in the 111 direction, but however, there is a tilt between the two, and the tilt angle can be deduced directly from these images, and it is 5 degrees. And the reason for this tilt is that it will increase the fit between the lattice of the oxide and the lattice of the metal. So this is a way that nature is using to minimize the interface energy, or to lower the strain of the interface. And 5 degrees is exactly the right angle that will minimize the mismatch between the lattice of the oxide and the lattice of the metal. Now we know, and this is not from STM, it's because we are always combining STM with XPS and other surface analytical techniques, but we know from XPS, and some others have also found that there is a layer of hydroxy groups adsorbed on the surface. And this is very important because an oxide often have a fairly high surface energy. This is not really the case for copper oxide, but we will see the next example that the surface energy of the oxide growing is very high, and the oxide should not be stable. But this direction of growth is stabilized by the adsorption of OH at the surface. So the key factors there are, one, that the passive oxide is crystalline, which was a new finding at the time where we did these measurements, because most people saw that passive oxide films were amorphous, and they were basing that on just measurements done on silicon dioxide at that time, because these films are very thin. The thickness here, you can see, deduced from the coulometric measurement, is just a few monolayers of oxide, so it's difficult to get X-ray diffraction patterns, except if you do grazing angle diffraction. But to do that, you have to go to a synchrotron, and actually there have been measurements also done on the synchrotron by another group who found the same structure as we had found already. So crystallinity of the passive film is a key feature for the stability of the film. Minimization of the interface energy by a growth tilted with respect to the base surface, and minimization of the surface energy. So these are 3 critical factors for the stability of the oxide. So this is the model of the surface here, and in addition, there are OH groups adsorbed at the surface. So we did similar work on other metals. I'm going to show 2 other examples to show similarities and differences. The next example is the case of nickel. So this time, we also use the nickel single crystal. So they both crystallize in the same system, the face-centered cubic system. So the starting surface has the same structure. We also use a 111 orientation, but this time we looked at acidic solution. And this is the polarization curve for nickel in this acidic solution, coming from slightly cathodic potential. You have a very high dissolution peak, so very fast corrosion, and above a certain potential, the current drops, and this corresponds to the formation of an oxide on the surface. And clearly, this oxide is protective because the current decreases a lot, and there is only a small remaining current in what is called the passive region for this metal. And what I'm showing here is one of many images that we recorded, and this was recorded at potential, which is indicated here, 0.85 volts. And again, there are two images here. One is on a fairly large scale, I mean, on the scale of a scanning tunneling microscope, 75 by 75 nanometer square. And this is the high resolution image, again, obtained in situ while we were polarizing the sample and measuring the Faraday current. We also recorded these images, and this is again a non-filtered image in the direct space from which we can deduce directly the structure of the oxide. So if you look at this image, you find again terraces and steps. So although again we start with a very smooth surface, so again the film, which is crystalline, is clearly not in perfect epitaxy with the substrate. It's in a tilted epitaxy with the substrate. The structure that can be locally measured with the STM is clearly, again, an hexagonal structure, and it corresponds exactly to the structure of nickel oxide, NiO, which is an oxide that crystallizes in the rock salt structure, the NaCl structure. What you can see also is that some of the steps are aligned and show perpendicular shapes, and some others do not. And as I will not go back to that later, I would like to point out that this is a very interesting feature, because from this kind of image, we can look as a function of time to the low dissolution that is still taking place in this range. And we can show how these steps evolve as a function of time at the applied potential. And if we do that, we found that steps that are rough are dissolving much faster than the steps that are aligned like this one. So this one would remain stable for a very long time, whereas the steps that are rounded would dissolve. And that's very important if you think about long-term usage of these metals, to know how this is going to evolve with time. Well, if you think, for example, of storage of nuclear waste for several 100,000 years, this is, of course, the kind of thing that you have to take into account, because changes at the atomic scale will matter on a very, very long time scale. So now, this was just about dissolution in the passive state. Now, if I come back to this film, so again, it's crystalline. It's highly crystalline, actually. It's in the quasi-epitaxy with the substrate, but only quasi-epitaxy, because, again, when you see that there is a tilt angle between the substrate and the oxide. And we could measure the tilt angle by looking at these images. And this is shown here. And actually, this is the superstructure of the oxide surface. And that's interesting because this oxide is also covered by a layer of hydroxides. And I would like to state there that normally nickel oxide does not grow in the 1-1-1 direction, which is, however, shown by this image, because nickel oxide is a so-called polar oxide. So in the 1-1-1 direction, it alternates planes that consist of only anions, and the next one is only cations. And this is completely unstable. This is called a highly polar oxide, and normally these surfaces do not appear. And we did the same experiment of oxidizing the same nickel in very high purity oxygen in the gas phase, and we never found this growing structure. But if we added a small amount of water to the oxygen, water vapor, then we found this structure. So a small amount of water vapor in the gas will result in the same growth of the oxide as in aqueous solution in that case. The other thing is that you see that there will be sites that are differing at the surface, and it's important at this point to know, for those of you who are not very familiar with the topic, that the enemy for these oxides are chlorides, chloride ions, because they will locally attack the oxide. And there are a lot of chlorides around us, especially in seawater. And chloride, and then from this kind of model, which is directly derived from the STM measurements, we could derive the proper DFT model to calculate and model and calculate how chloride ions could replace these OH ions that are formed at the surface. And the last example I'd like to show for pure metals is the example of chromium. So once again, this is in acidic solution. This is the polarization curve with a dissolution and then passivation. And we looked at this potential, and this is the image that was recorded. So again, you can see terraces, steps, highly crystalline oxide according to the high resolution STM image. And again here, the oxide, you see the hexagonal structure. Now chromium is not a face-centered cubic metal, it's a cubic center metal, so that's the reason why we use the 110 surface. And you see that here, it has an hexagonal structure which is typical of the basal plane of chromium oxide, which has the same corundum, the same structure of aluminum oxide, alpha aluminum oxide, which is the corundum structure. So again, it's the basal plane that is growing. So again, it's the one that has the lowest surface energy. And same with nickel with the OH. And again, I forgot to mention that there is also a tilt that we calculated of 3 degrees, and which gives the best match at the interface. So we always find these key features for the stability. So they are summarized here. What are the atomic level features of passive films on metals? Passive films are generally crystalline, because there are exceptions. Epitaxial growth is observed, but as I said, it's a quasi-epitaxial growth. The interface energy is minimized by the tilted growth, and the surface energy is minimized by the hydroxylation of the surface. So these are the key features, and in principle, passive films that would have these characteristics would be a good passive film and will protect a surface against corrosion. Now, we don't use so much pure metals, at least for engineering materials, but we often use alloys. The reason is that then we need to have a good compromise between mechanical properties, chemical and corrosion resistance properties, and cost, of course. So stainless steel is a good example of a commercial alloy that is widely used. I think you are still all using stainless steels in one way or the other. So we were looking at an alloy, two alloys. We are looking at binary iron-chromium alloys and the ternary iron-chromium-nickel alloys. So these are single crystals. Of course, these are not the commercial alloys, but they have the composition very close to the composition of commercial widely used alloy. This one has an austenitic structure, and this one has a ferritic structure. And this one is usually considered as having a better resistance to corrosion than the ferritic counterpart. So to make a long story short on that, we did the same kind of work as before. So this is the high resolution STM image, where again you can see a structure which is an hexagonal structure, and the model for that is again the basal plane of chromium oxides. So as for the pure metals, the film is crystalline. It has the same atomic structure as on pure chromium, but it has a different composition. And from XPS, we know that it contains actually a lot of iron, which is not surprising because iron is the base metal for this. So what we were interested in was the aging of this passive film. Does it crystallize readily? How does the structure and composition evolve with with the potential and time? So this is a series of STM images taken at different lengths of times. This is after 20 minutes, and you can see that the surface is very disordered. So at this point, the film is not yet crystalline. After 2 hours, we start to see these nanocrystals. Look at the scale. This is 1 nanometers. So these are nanocrystals of essentially chromium oxide with iron in it. And after 20 hours, the whole surface is fairly well crystallized, and this is the same type of image. So crystallinity is enhanced actually by aging in an aqueous solution, which could have been a slightly counterintuitive, but this is the result. Crystallinity is enhanced, and also increasing the potential. I'm not showing data here, but increasing the potential also enhances the crystallinity of the oxide. And we have suggested the interpretations for this effect in a few papers. So these films should be very good. However, these stainless steels that are normally well protected against corrosion, they do show localized corrosion problems if they are in an environment that contains aggressive ions, such as chloride ions or halide ions in general. So the big question is, what is the exact nature and origin of the weak points in these films that make them susceptible to localized attack? And we address this fairly fundamental question by asking ourselves, can the oxidation process itself produce these weak points? Because we start with a high purity single crystal, we can control the conditions of formation of the oxide, and however, there are still some weak points. In the past, these weak points were just inclusions in the stainless steels. You know, there were sulfide inclusions, so corrosion would always start at inclusion. But nowadays, this material, industrially produced, are very pure, and they still show some cases of localized corrosion. So this is the question we were asking. And it's not easy to answer this question, because one would have to look at the very, very early stages of formation of the oxide. And this can only be done if we can start with a completely clean surface. And as you can guess, reducing chromium oxide is not an easy task. So to do that, we had to use a new system to investigate the genesis of these weak sites in surface oxide films. And namely, this is the instrument that is shown here that combines different techniques. It combines a chamber for the surface preparation in UHV condition or gas. We can do thermal treatments, we can do diffraction, and then it combines inside the same equipment, we can transfer samples to an STM in which we can vary the temperature. We can also introduce gases. And there is also an in situ XPS, in situ, not in aqueous solution, but we can introduce a gas and look in situ at what takes place. And finally, there is a glove box in which there is an electrochemical cell fitted with an electrochemical STM. So in the same equipment, we can look at the surface and move the sample from one chamber to the other, depending on what we want to do. So what we could do using this instrument is that we could start with a very clean surface of single crystal stainless steel. At this point, we discover that actually the clean surface has vacancies, ordered vacancies at the surface. And then we could look at the oxidation in situ. So we saw that the key is in the early growth of the oxide, and to do that, we used oxygen gas. And it's only when we understand the system that we look at what happens in aqueous solution, because in the aqueous solution, it's not possible to prepare a surface, an initial surface that would be completely free of oxide in an aqueous solution. So these are measurements that are done, real-time measurement in situ in the XPS, where we expose the surface to oxygen, and we can look at the oxygen 1s. So this would be the intensity of the oxygen 1s signal as a function of time during the oxidation. So this is an in situ measurement, and this is a plot of the intensity of the oxygen as a function of time. And you can see that at room temperature, it would reach a plateau for extremely low exposure of oxygen. And that would be very short time. What we did here, we reduced the pressure of oxygen to a very low value in such a way that it would take more time to oxidize. But if you convert this scale, which is in Langmuir, 1 Langmuir is 1 atmosphere multiplied by 10 to minus 9 seconds, it would mean that this scale, which is in Langmuir, if you convert it to what happens at atmospheric pressure, this scale would be in nanoseconds. So you see the speed at which these materials are oxidized. And now, I have to go fairly fast, I'm sorry for that, but we looked at different exposures. We looked at the XPS, and what we found, which was known already, is that there is, of course, a preferential enrichment of chromium-3+, and at the beginning, only chromium-3 oxide is forming. And it's only later that the iron starts to be oxidized. So at the very, very beginning of oxidation, the film consists of only chromium oxide, and iron oxide arrives later when there is not enough chromium to sustain the growth of the oxide. And we could look at that with high resolution STM, starting from this surface that has only metal and an ordered array of vacancies, and exposing it to oxygen. This is after 1 Langmuir, so it would be the equivalent of 1 nanosecond at atmospheric pressure. Then you can see at the steps here, formation of these nuclei of oxides, which according to the XPS would be chromium oxide. And the terraces are not yet oxidized. So the nucleation takes place at the side of these steps. And if you look at the high resolution, you see that the chromium oxide is nucleating along these steps, and they are called multi-steps because they are more than 1 atomic distance in height. And you can see also that the vacancies are completely modified at the surface. And if you look in details at the arrangement of the vacancies, we can conclude that what is going on is that chromium, the vacancies are moving away from the step H, and this allows chromium to go and nucleate the oxide. So there is a mechanism that was revealed by this work by which chromium is pumped to the step H to form the nuclei of chromium oxide. And of course, you can anticipate that this is surface diffusion. There is no bulk diffusion. This is surface diffusion. So you can anticipate that because chromium is pumped, it will be primarily pumped from the near edge, so that there will be areas here which will become depleted in chromium and enriched in iron oxide. So the guess is exactly what happens. If we continue the oxidation further after a longer exposure, we see more chromium oxide nuclei everywhere on the terraces, but near the step H, we have this fine structure which, you have to believe me, can be assigned to iron oxide. And it is not only in that case from these images, but some other people have looked at iron oxide, and this can be unambiguously assigned to the formation of iron oxide. So the mechanism here is pumping of the chromium in the early stage, and then formation at very local points, that is at the atomic scale or nanoscale, formation of an iron oxide, which is not good as a passive layer. So we believe that this is really what happens, and that is the genesis of these weak points in passive oxide layers. So the oxidation process itself is producing these chemical heterogeneities. So this is summarized in this sketch. Early stage pumping of chromium to the step H with formation of chromium oxide, formation, modification of the array of vacancies, enrichment or depletion of chromium in the area near the edge, where the iron oxide will start to form. And then if you continue the exposure, well, the chromium oxide will continue growing on most of the surface, but at areas where the iron oxide has nucleated, it will continue to grow, and it will form these nanometric weak points in the oxide layer. So if we now predict what will happen if we expose a surface like that to an aqueous environment containing aggressive ions, we expect that there will be a localized attack at this point and not at this point, because we know that a pure chromium oxide layer is not attacked by the chlorides. So we did the experiments, and this is what we observed. So this is now the same, it's not the same sample, but it's the same stainless steel, same orientation, exposed to sulfuric acid, and you can see this image. If we zoom on one of these chromium oxide islands, we find again what I have shown before, a pure chromium oxide, but you see that there are areas where you have these depressions, and we assign this depression to the spots where we have nucleated iron oxide. So it's the oxidation process itself that is creating the defect. So how can we heal this defect? So now we have understood the phenomenon, but what is the solution? Well, the solution could be, and this is what we are looking at the moment, the solution could be to add another alloy element that would react with the small iron oxide islands that are responsible for the localized attack. And to do that, we looked at a new class of alloy, which are called high entropy alloys. Basically, these are alloys that contain more than 4 or 5 elements with nearly atomic concentration. And the idea, based on thermodynamics, is that if you do that, you increase the entropy of the alloy, and you can stabilize phases that would otherwise be unstable. So it's a sort of hot topic for the metallurgist. So what we saw is that we could then produce an alloy that would have more molybdenum and keeping a single phase, because we don't want to create structure heterogeneities in the alloy. So in collaboration with the metallurgy lab in Thiers in France, we designed these alloys, and they made it. So they did also the thermodynamic calculations. So we've been looking at an alloy that you see contain 5 elements, not exactly equimolar, but almost for the chromium, iron, cobalt, nickel. And then we have a fairly high content of molybdenum, 5 atomic %, which is something that you cannot achieve by classical synthesis of alloys like stainless steels. And then to make a long story short, because I'm surprised that the chairman is very quiet, but if I were the chairman, I would already have said, please conclude. So I'm telling myself, please come to the conclusion. So we passivated this alloy, and I knew that I would have little time when we arrive at this slide, so I've put all the results in one slide, and I'll go quickly. We did XPS, and after passivation of this alloy in acidic solution, and we looked at the molybdenum, and indeed, in addition to the metal, we can see peaks that can be assigned to molybdenum oxide with 2 chemical states, molybdenum 4 and molybdenum 6. And then we used another techniques, very powerful techniques, which is a time of flight secondary ion mass spectrometry that allows us to look at ions emitted under the effect of a primary beam, and we can sputter the oxide and make depth profile. And we use a time of flight since, because this allows us to record all the elements of the periodic table plus molecular ions in one experiment due to the time of flight analyzer. So here I've shown, and there's a mistake here, I'm sorry, the blue curve is for an iron oxide ion. So you can see that there is mostly chromium oxide, as I have shown before. and there is some iron oxide at the surface, but also in the oxide, a small amount, which corresponds to the mechanism I have explained before. And if we have molybdenum, and we have normalized the curves because there are not a huge amount of molybdenum, so it's normalized. You see that the molybdenum is found in the inner part and also near the interface between the iron oxide and the chromium oxide. And that's where these weak points emerge at the interface. And if we look at the corrosion behavior, these alloys have an extraordinary resistance to corrosion. You can add up to, in an acidic solution, we could add up to 5 molar chloride, which nearly no existing alloy would stand, and have absolutely no change in the electrochemical characterization. And this is the model. So you find again the oxide layer. On top there is a layer of hydroxide that I've not talked very much about this layer because the barrier layer is this one. This would be the weak points that we have detected by looking at the early stage oxidation, and they would be healed by the molybdenum. So the story is complete. We've looked at the passive films on pure metals. We've looked at the major characteristics. We've looked at alloys, and then the question was, why do we still have weak points? And we have elucidated the genesis of these weak points formed by the oxidation mechanism itself. And there is a solution. Of course, this needs to be refined to come to a solution that could be adopted by the industry. So just a general conclusion here to reemphasize that the structure reactivity relationship at the atomic or nanometric scale is really a key to the understanding of corrosion phenomena and the development of corrosion-resistant materials. And also, I hope that I've been able to convince you that we've made significant progress by using this surface science approach in which we combine surface chemical and structural characterization in situ with the STM, ex situ with the other surface spectroscopy, and combining that, of course, with electrochemical measurements, and although not shown here, combined with modeling, which we do a lot using DFT. And with that, I would like to just show you a photo of my group, not very far from here. This is Rue Pierre et Marie Curie at Chimie Paris-Tech, and you can see, this is behind the Marie Curie Museum, so you can see Pierre and Marie Curie that should inspire us all. And thank you very much for your attention.